Hello everyone. Today I'm gonna go over chapter 13 of our course. It's all about vector functions. Alright, so let's start with 13.1. I'm gonna go over some introduction of what it means by vector functions. Let's start with the function R. Is x, y, z, right? It's in 3D. So R is a vector. Be expressed this way. Oh, it's gonna be angle bracket this way. Okay. Now, in terms of function means what? When R changes in terms of t, you think of x. The x coordinates as a function with respect to t. Y is also a function with respect to t, and the z is a function with respect to t. And we call it the vector function. Okay. For example, RT is equal to cosine t, comma sine t, comma, say 0. So actually this is, you graph this one, you have a circle. Okay? Circle is on the xy planes. It's cosine squared plus sine squared equal to 1. Circle with radius 1. What if I put it to t? So this means what? Xt is equal to cosine t, yt equal to sine t, and zt equal to t. Okay? Where t is any real number from negative infinity to positive infinity. And this is another function. Okay? And you guess what? This graph will be something called the helix. It looks like the spring. It looks like this. Alright, so when t changes, right, the x and y coordinates vary between -1 and 1, and t keep going to from negative infinity to positive infinity. So it looks like a spring. Upward like this. Okay? So this is the idea of a vector function. Right? Introduction. This actually is all about section 13.1, and I can talk a little bit more about this. A function is continuous, or you will talk about take the limit. All right. So you take the limit of R of the vector when t goes to some value, say a. Actually, you all we have to do is take the limit of the x component, take the limit of the y component, take the limit of the z component. That's it. So in general, this is equal to, say, the limit of x, when x go to a, and then the limit of y also go to a, and then the limit of z, limit, right? The limit of z, where z go to a. Another word, think of a vector function is a combination of coordinate function of all the coordinates, x, y, and z components. Just simply do one at a time. Okay. And we talk about continuity. It's the same thing. If vector RT is continuous at t equal to a, means what? The x component is going to be continuous, the y component is going to be continuous, and the z component is going to be continuous at that point. All right. So for continuity, it's the same thing. Let me just write it down here. It is continuous if continuous at t equal to a. That means the limit of f of t, oops, going to be r of t, right, instead of function now. Use vector r for function. T approaches a is equal to r a. Okay. So let's talk about just one component. This is t right here. When this is f of t, right? One component. Okay? When t right here. When oops, t right here. T approaches a from the left or from the right. This is f of t equal to f of a. This is count 1. Whenever there's another one, there's no hole, no gap in between at that point locally. That's open interval close to the point and say continuous. Anyway, in count 1, we learned what? A function is continuous at a point if the limit of the function, when t approaches to that point, and a is equal to the point. Means what? It's a solid dot. And we just carry over to three-dimensional space. So it's not a new thing, so I don't want to go over this one more time. You can look up in the book for this definition again. Okay? And now we don't just talk about continuity, we can even apply what? Derivative or integral. All right, so let me rewrite the vector function one more time. So you got RT is equal to what? XT, YT, ZT. Actually, they put it to 13.2 already. It's still talking about vector function. So R prime of t, oh, by the way, this is one of the way to denote derivative, or you can write this way, d over dt of vector RT. Leibniz notation either way represent the derivative function. And guess what? You want to take the derivative of vector, you just simply take the derivative of all the components of that vector. So what? X prime t, or you can write what? dx over dt, okay? Or what? Y prime t and z prime t. Simple. Alright, so example. Let me use the same example that I gave you minutes ago. RT equal to cosine t, sine t, and t. And R prime is what? Derivative of cosine is negative sine t. Derivative of sine t is cosine t, and derivative of t is 1. This is derivative. And by the way, this is what? Later on, of course, in this chapter, you see what? If you think of this is the distance function, okay, position function, and this is gonna be what? The velocity. And guess what? If you take the derivative of velocity, you're gonna get what? The acceleration. Okay. And think of t as a time. Okay. So this is what? Recall back to count 1. You have a function. If you take the derivative of the function, what you got? The slope of the tangent line, right? So in terms of vector, this is a curve in the 3-dimensional space, and this is what? The tangent vector. It's also a vector, okay? The tangent vector means what? The vector that is tangent to the curve at that point. All right. We can talk about integral as well. So integral of RT. Now what? This is RT, right? Integral. So you have to write dt here. It's what? Integral of all the components. Integral of xt dt, comma integral of yt dt, comma integral of zt dt. And then one vector function now can be interpreted what? 3 integral function of 3 components, x, y, and z coordinates. That was the idea. So it's not hard, but I think it's more work because instead of doing one integral right here, you actually have to work with what? 3 integrals if you're talking about 3D, or 2 integrals if you are doing 2D. 2D means 2-dimensional space. Okay? Oh, what if you have the boundary, say from A to B, and of course, nothing special, A here to B there, A here to B there, A here to B there. Okay, and then you have to calculate the numbers for each integral. So that's kind of trivial. All right, let me see if I missed anything before I move on. Okay, show you a bunch of formulas about derivative and integral. And you guys seen this before in terms of single variable function. So you write in terms of vector. So say if you have vector u plus vector v, write the variable. ut plus vt, okay, and then you take the derivative. It's a sum, right? Sum of the derivative equal to u prime t plus v prime t. Those are the same thing. So instead of talking about 2 functions, now what? We're talking about 2 vector functions, but the idea carries over. Exactly the same. Okay? What if you have a constant? Say c is a constant times vector u, and then you take the derivative. You leave the constant alone. You take the derivative of vector u. Right. What about the product rules? We have several versions of product rules. So you got a function f of t. Okay, this is one variable function times the vector u of t, and then you take the derivative of the whole thing. Carry over the product rule. What? derivative of the first, so f prime of t. Keep in mind that this is what? The derivative of a single variable function, okay? Time vector ut plus f of t times vector u derivative. See? Derivative of f times u plus derivative of u times f. Okay. One more. How about dot product? Now I got u vector dot v vector. And then I take derivative. Same rules. U prime dot v plus v prime dot u. Let me just write in the same order so I can carry over for the cross product. Okay. So derivative of the dot product is what? Derivative first times the second plus the derivative second times the first. But I'll try to preserve the order so I can carry this over for the cross product. And let me use red marker for that. If you got cross product, it's gonna be the same thing here. Oh, not here, okay? Here. And one thing about the cross product is what? Order is preserved in the cross product. So if you write u on the left, v on the right hand side, then what? When you take derivative, make sure that everything is in the same order. So u prime on the left, v on the right, u on the left, and v on the right, always. All right. Last one, the chain rules. So instead of having u, function u with variable t, what if you got, where's my mouse? Right here, vector u with the variable, say f of t, and now you want to take the derivative. You see that the variable for u is not t anymore. The variable for u is f of t, right? And of course, it's going to apply the same rule for the chain rules that we learned before. This is what? F prime of t times u prime vector of f of t. Just simply carry all the properties that we learned over from cut 1. Okay. And we talked about integrals already, and it's the same thing. Let me just try to give you an example. Integral. So ut. I'm going to do the same thing because it's simple. What? Sine t, cosine t, and t. Okay. Now it's another helix, but now x is sine and y is cosine. Still the same helix. All right. And I want to integrate this. Integral of vector ut dt. Then what? I'm going to integrate sine of t. Integral of sine t is negative cosine t plus, say, c1, comma, integral of cosine t is sine t plus c2, and integral of t is 1/2 t squared plus c3. Right? Remember, when you do the integral, don't forget to add a constant, and I want to distinguish between the 3 constants I call C1, C2, and C3. Or you can write this way, cosine t negative, right? Integral of sine is negative cosine, comma, sine t, comma, 1/2 t squared plus what? C1, comma, say comma, C1, comma, C2, comma, C3. Or usually people write this way, negative cosine t, comma, sine t, comma, 1/2 t squared plus vector c constant. Okay? This c here means what? C1 plus C2, C3. So I try to emphasize what? Integral of vector is going to be equal to another vector plus a constant vector, just like a constant number when you guys integrate one variable function. All right. So we are at the first 2 sections of chapter 13, section 13.1 and 13.2. We are trying to introduce to you guys the vector function. So pretty much, vector function is a function of 3 function of the coordinates of the components. So pretty much whatever you do with the vector, say take the derivative, you do the integral, pretty much you apply all the work into each component. Okay? You take the derivative of the whole function, you take the derivative of each coordinate, you integrate the whole vector, means that you integrate each coordinate. And all the product rules and the power rules and the chain rules gonna apply. We don't divide vector by another vector, so we don't have the quotient rule in here. All right. And that is the end of the first two sections. Let me move on to some real math in chapter 13. Okay. So in here, the vector function is a short way of representing what? A curve on the three-dimensional space. Okay, this is RT. One thing that we learned, the first thing we learned on 13.3, section 13.3, is something called the arc length. Arc length. We call it 2D. We learned in count 2, I think the arc length is L. Say I have a function in two-dimensional space. I want to calculate the arc length when I say x run from A to B. It's going to be the integral square root, right? 1 plus f prime square, and then dx on the parametrics run from A to B. Or when t run from t0 to t1, you talk about t and integral from t0 to t1 integral. This is a review from count 2, okay? X prime t, or dx over dt is the same thing. X prime t square plus y prime t square dt. Okay? And if you think of this as a vector with the r is equal to x comma y, or x t y t, then this is no more integral from t0 to t1. This is what? The magnitude of r prime t dt. Because r prime is x prime comma y prime. Okay. I'm going to use this notation for a vector. So the magnitude of r prime is going to be square root of x prime square plus y prime square. Okay. And this is the arc length from one point to another point in the 2D. And you can, the whole formula is going to carry over to 3D. Or right down here in 3D. Guess what? We just add one more component into it. Now, your vector RT is XT, YT, and ZT. Okay? So since it's 3D, I cannot use the variable x anymore. I have to use the parametrics equation. So t is a variable. Then R prime t is x prime t, we learned this a minute ago, y prime t, and z prime t. And the arc length is calculated this way. The length, when t runs from one point to another point, okay? So you have a curve. I just erase it, so let me rewrite it in here. You have a curve in 3D. Anything. Run from t0 all the way to t1. How do you calculate the arc length? L is integral from t0 to t1 and square root. Well, so instead of having just the derivative of x and the derivative of y, we have z in here. So what? X prime square, y prime square, and then z prime square. dt. Or in short, you guys can write this way: integral from t0 to t1, magnitude of r prime t dt. Because this is really the magnitude of r prime. Okay. Recall one formula that I gave you before, and I claim it's pretty useful. Say you have 2 points on three-dimensional space or two-dimensional space, doesn't matter, and you want to calculate the line segment. we have a formula for line segment. What was RT with 1 minus T R naught. This is from R naught, okay, all the way to R1 plus T times R1. I'll just try to write it down one more time. So it's help you to get it better than whatever R naught they give you, whatever R1 they give you, you can put it in. Say for example, I give you R naught as say 1, 0, 2, and R1 is at 0, 1, negative 1. Okay. Then vector RT is what? 1 minus T, 1, 0, comma 2, plus T times 0, 1, negative 1. Right? And then you can simplify. You got what? 1 minus T, comma 0, comma 2 minus 2T. You see what I did? I multiplied 1 minus T to every single component. Plus 0, comma T, comma negative T. Now you add them together. 1 minus T plus 0 is 1 minus T. And then 0 plus T is T. And then 2T minus 2 minus 2T minus T is 2 minus 3T. And this really gives you the vector function where x equal to 1 minus T, y is T, and z is 2 minus 3T. Right? And this is really the equation of the line segment from R0 to R1. And in this formula, the condition is what? 0 less than or equal to T less than or equal to 1. We just include here, start with T equal to 0, and we end it here with T equal to 1. And if you go from here to there, it's going to go backward. Okay, and that is the Euclid formula to calculate the length of the curve. And this particular example is the simplest one. Is what? A straight line. Okay. And actually, I claim that you have 2 points. You want to calculate the point from here to here. You can actually just use what? The distance formulas. Remember, square root of x1 minus x2 squared plus y1 minus y2 squared plus z1 minus z2 squared. You have the answer. It's exactly the same. All right. Let me rewrite the formula right here. The arc length formula is what? L is equal to integral from T0 to T1 square root, right? X prime T square plus Y prime T square plus Z prime T square dt. All right. Now I'm going to talk about something called the arc length function. Think of it this way. Say you have a curve. Okay. This is T0, and this is T1. And I can calculate the exact arc length of that curve from T0 to T1. Now, I want to think of T1 as a variable. So whenever I change the value of T1, T1 is right here, I got the arc length. If I move T1 over here, I got another arc length. Okay? So think of T1 as a variable, then it turns out that what? The length is not a fixed number anymore. It depends on the value of T1. You have a new arc length. So this L now is a function of the variable T1. If T1 change, we fix T0, okay? We fix the initial point. And whenever we change the value of T1, we're going to have a new arc length. And this is all called what? The arc length function, because it has a variable. Okay? So instead of having the fixed length all the time with your fixed T1, then you have a fixed length. But you change the value of T1, you have a different arc length. And then now it becomes a function. But people, just our habit, our tradition, don't use T1 as a variable. But we change it into a different letter. But it doesn't matter, it's the same. Okay, and here's the version of the book. So they want to use T as a variable. But the problem is, if you use T as a variable right here, it's gonna get cumbersome. It's gonna get confusing with the T value that we use inside the integral. And we know the variable we use inside the integral is just the dummy variable, so it won't change anything. So first of all, we're gonna change it into a new variable. U u, and u, and the formula is exactly the same. Okay? Now, we don't have t inside. So instead of using t1 as a variable, we call it t. Now, this looks like our book version saying what? The arc length as a function of variable t, where t is the upper bound. Well, whenever t changes, you have the new arc length of the curve. Depends on the value of t, you have the new length. And that's called the arc length function. All right? So let me talk about, we're done with the arc length. Let's talk about something called the curvature. Curvature is denoted by kappa. Okay, this is a Greek letter for K. I'll walk you step by step to get there. First, we start with the vector function, RT. We learned this already. This is what? XT, not vector in here, YT, and then ZT. Okay? It show you whenever you plug in a value for T, you're going to have a point on the plane, on the three-dimensional space. I mean, on the space, not the plane. All right? Now, if you take the derivative of this, R prime, what you got is x prime t, y prime t, z prime t. And guess what? Like in the one-dimensional space function that we have, this is the tangent, right? When you take the derivative of the f, you got f prime is the slope of tangent line. This is the tangent vector. Try to explain to you right here. Let's say you have a curve, have a point right here, RT. You take the derivative. This vector is r prime t. Okay? Tangent to the curve at the given point that you are taking derivative. Okay? Now, r prime t could be a long vector, could be a short vector, who knows? But for sure, it's going to be tangent to the curve. And now, instead of working with long or short vector, we define something called the tangent vector. We're going to make all the tangent vector becomes a unit vector. Unit means what? The length 1. And how you're going to make a unit vector from a given tangent vector? We're going to divide the vector by the magnitude of that vector. So vector t, t stands for tangent, of the variable t is equal to r prime of t over the magnitude of r prime. And this is going to give you the unit tangent vector. Let me change it a little. It's going to be unit tangent vector. Unit tangent vector. Okay. Not just a tangent vector, but it's also have the length 1, because I divided by the magnitude of the tangent vector. This is a tangent vector, and whenever you have any vector, you divide it by its magnitude. You have same direction vector, but got unit 1. Okay, got the length 1. And that's called unit tangent vector. Okay? So R could be that short, could be that long, who knows? But we're going to make it tangent by divided by 8 length. So all the tangent vector now, well, that's a short way of unit tangent vector. All the unit tangent vector now are going to have length 1 and tangent to the curve. Okay? And this is going to be easier for us to work with. So we define something called a tangent vector. Okay? Or unit tangent vector. Now that we have a unit tangent vector already, we're going to define the curvature. Curvature. Kappa, K, K is equal to the change of tangent dt over the change of the distance. Okay? So what does it tell you? You see? Curvature is a number, okay? It's tell you how sharp of a turn.